In the next portion of the lecture, I'll talk about a different kind of model called an autoencoder. Now, autoencoders are a very widely used class of models for all sorts of unsupervised learning tasks. Not all autoencoders are generative models. In fact, the autoencoders that we'll discuss today are difficult to use for generation. But we'll talk about a special kind of autoencoder on Wednesday called the variational autoencoder that is actually a very good generative model. Since autoencoders are such a old and widely used class of models, much of this part of the lecture will actually be a little bit of history about the types of models that people have explored in deep learning. Some of these models can be used today, although they're generally not the best performing or the most effective models. But I think it's important to discuss this topic, partly to provide a little bit of perspective on where some of these ideas come from, and partly to provide the foundations that we'll need to understand more modern autoencoder architectures, which we'll talk about later. Okay, so let's start with a very, very high-level view of probabilistic unsupervised learning models. For example, things like language models. At a very high level, you can think of them as having inputs where the input corresponds to the image, the pixels in the image. Now, those pixels have to be ordered in some way, but the whole image is there. The whole image serves as input. And the goal is to produce that same image. But in the middle, you have some structure that makes this task of reconstructing the image somewhat non-trivial. So the particular structure that you have in a pixel RNN, for instance, is that the pixel RNN doesn't get to look at pixels that it hasn't generated yet. So it has to generate a pixel before it actually sees what that pixel is. So for example, pixel 1, 2 has to be generated at time step 2, and then it serves as input only at time step 3. So in this case, the structure is the fact that each pixel has to be constructed from preceding pixels. If this structure wasn't there, the task of mapping an image to itself would be trivial. Similarly, something like the image transformer also takes the entire image as input, and it produces the entire same image as output, but because it uses masked self-attention, that imposes structure which makes this problem of mapping an input to itself non-trivial. This is a good time to think back to some of the things we learned about when we talked about language models, things like BERT, right? There, with BERT, to construct a bidirectional transformer language model, we had to confront this problem head on. We had to ask, what kind of structure can we impose that makes mapping a sentence to itself non-trivial? And we learned at the time that if you just use a regular non-masked self-attention, like you would have in a transformer encoder, then BERT's task would be trivial. So therefore, BERT uses this per token masking to impose structure. So 30,000-foot view, the input is the image, the output is the same image, and there's some structure in the middle, and that structure makes the problem of mapping the image to itself non-trivial, which forces the model to learn meaningful representations. So you can think of this as a general design for generative models, or more broadly for models that can be used for unsupervised learning. You have some input, which could be an image, a natural language sentence, a vector, whatever you have. It goes into a model, and that model has a loss, which is to produce the same thing as output. So the model's loss is to basically reconstruct whatever came in. And an arbitrary model could just learn the identity function, but some kind of structure is imposed on the model that makes this task of reconstructing the input image not easy, not trivial, which prevents the model from learning the identity function and forces it to learn meaningful representations. Examples of structure that we've seen: RNN or LSTM sequence models that have to predict a pixel's value based only on previous pixels, pixel CNN models that must predict a pixel's value based on a masked neighborhood, pixel transformer, which makes prediction based on masked self-attention. Now, all of these models have spatial structure, right? The additional structure is spatial in nature. It has to do with the arrangement of the pixels in the image or the arrangement of the words in the sentence. But can we use more abstract structure? Once we recognize that all these models basically read in X and then output that same X and then have some structure in the middle, can we change that structure in the middle to something more abstract? So more broadly, models that take in some input and then are tasked with producing that same thing as output are called autoencoders. And the principle, the basic idea behind an autoencoder is to train a network that encodes an image into some hidden state and then decodes that image as accurately as possible from that hidden state. Such a network is called an autoencoder, and it needs some kind of structure to force the hidden state to be meaningful. So the general recipe for an autoencoder is that you have an image, it's fed through some neural network that we call an encoder, and then we have some kind of intermediate representations, activations in that network, which we call the hidden state, and then a decoder takes that hidden state and produces the same thing as output. And all these language model type things that we saw before have this kind of sequential structure to them. Now we're going to dispense with the sequential structure completely. We're not going to have the sequential stuff. And we'll talk about other simple principles that we could use to force structure on the hidden state. And the hidden state is what we're going to actually use for downstream tasks. So the goal of the autoencoder is to acquire a hidden state. It's basically a representational learning goal. Once we've acquired the hidden state, then we can use it for all sorts of things, like training classifiers and so forth. So something about the design of the model, or something in the data processing or regularization, has to force the autoencoder to learn a structured representation. And what we're going to do in this part of the lecture is we'll talk about different kinds of structure and different mechanisms for forcing that structure that people have tried in the past. And some of these methods will be kind of more for perspective, like they're not really used all that much today. And some of them are actually still widely used, although maybe not the most kind of cutting edge approaches. Okay. So one approach to forcing structure is limiting dimensionality. Make the hidden state smaller in terms of the number of dimensions than the input or output, so that the network has to compress the input or output. So if your input has 32 by 32 images, and your hidden state has only 16 dimensions, now you have to somehow represent the entire image with 16 numbers, and that dimensionality reduction might lead to more meaningful structure. Another thing you could do is sparsity. Force the hidden state to be sparse, meaning that most entries in the hidden state are 0, so the network has to compress the input. This might seem a little peculiar at first, but I'll describe the intuition behind this shortly. Another one, which might seem peculiar and counterintuitive, but is actually very effective, is to corrupt the input with noise, forcing the autoencoder to learn to distinguish noise from signal. And then the last one, which is something we'll actually talk about in much more detail on Wednesday, is to force the hidden state to agree with a prior distribution. This might seem a little weird, and if this doesn't make sense to you, don't worry about it. We'll talk about it much more on Wednesday, but this is actually the approach that we can use to get autoencoders to also be very good generative models. Okay, so let's start with the dimensionality, the simplest one. This is sometimes called a bottleneck autoencoder. It's one of the most classic types of autoencoders. The idea here is, whatever the dimensionality of your input is, you pick the dimensionality of the hidden state to be much smaller. So if you have a 100 by 100 pixel image, it has 10,000 dimensions, limit the hidden state to have only, let's say, 128 dimensions. So it can't possibly learn the identity function because it can't store the values of every single pixel in those 128 dimensions. This is very straightforward, and it does have some interesting properties. One interesting mathematical fact, which I'm not going to have time to prove, but it's true. If both the encoder and the decoder are linear, meaning they're not neural networks, they're just matrix multiplications, then training this kind of bottleneck autoencoder with mean squared error for reconstruction exactly recovers principal component analysis, where the dimensionality of the hidden state is the number of principal components that you're going to get. This might seem surprising, but it's actually true. So in a sense, you can think of a bottleneck autoencoder as a kind of nonlinear generalization of principal component analysis. So you can view it as basically nonlinear dimensionality reduction. And it could be useful simply because the dimensionality of the hidden state is lower, and then you can use various algorithms that are only tractable in low-dimensional spaces. Generally, from my experience, the kinds of representations that you get by training bottleneck autoencoders are not necessarily very useful in the sense that they don't tend to disentangle underlying factors of variation. They're not necessarily really good for, let's say, downstream classifiers. But just the fact that you can reduce dimensionality can be very useful to some applications. And it's a very simple way to do nonlinear dimensionality reduction compared to some of the alternatives. Now, today, I should say this kind of design is considered to be rather antiquated and is not used very often, but it's good to know about, and maybe if at some point you do need to get your data to be much lower dimensional, you might find this to be useful. So just to mention one classic application of this approach, this is actually a paper on reinforcement learning from 2012, where the goal was to control a little slot car, so it's a little car on a track, where you use a game controller to increase or decrease the speed, and you have to race the car around the track, using images. And the way that this algorithm worked is they take images of the slot car, they train a bottlenecked autoencoder, which actually autoencodes the images into a very low dimensional feature space, just 2 dimensions. And once they encode it down to 2 dimensions, they actually discretize it and run a very simple, very effective Q-learning style algorithm in this low dimensional space. And this allows them to essentially do RL on images. This paper predates most of the more sophisticated deep RL methods that we discussed before the break. Okay, so that's autoencoders with dimensionality reduction. Now let's talk about the second kind of structure, sparse autoencoders. These are a little bit more sophisticated. They're still not used as widely today, but they're worth knowing about, and they have some interesting connections also to neuroscience. So here is the basic principle. Can we describe the input with a small set of attributes? So the idea is that if you have a description of an image that is like, pixel 00 has this color, pixel 01 has this color, pixel 02 has that color, etc. This description of an image is complete in the sense that it is sufficient to fully build out the image, but it is not very structured. It's not very interpretable, and therefore it's probably not very useful for downstream classification. If instead you had a description of an image that was something like, well, whatever is in this image, it has ears, like the has ears feature is true, the has wings feature is false, the has wheels feature is false, etc., etc., etc. Basically, if you have a long list of all the possible attributes that a thing in an image could have, and each of those attributes is like either 1 or 0, this is perhaps more useful because then you could say, well, dogs are everything that has like ears, no wings, no wheels, and flop, and cute puppy eyes or something, whatever. You basically have attributes that describe dogs, right? An interesting property of these kinds of representations is that most attributes will be 0 for most images. Why is that the case? Well, because there are a huge number of possible objects in the world. Each of those objects has a huge number of possible attributes, and most objects do not have most attributes. So if I were to list like all the possible attributes that an animal could possibly have, and I show you a picture of an animal, chances are it only has a few of those attributes. And that actually goes hand in hand with the structure. So the sparsity principle says that what you want is this kind of attribute dictionary. It's very structured, and it will tend to be sparse because most objects do not possess most attributes. Most values are 0. And that's actually really neat because then the attributes that are present are very specific to that object, they're descriptive of that object, and therefore they are good for recognizing objects. So this is a somewhat more nuanced concept than just minimizing dimensionality, but it's actually a really powerful concept. So the takeaway from this, after we've gone through all this somewhat laborious logic, is that if we can somehow pull out a representation of images that is sparse, meaning that for most images, most features will be 0, we have good reason to believe that such representation will actually be very structured because it will intuitively try to represent images with these attributes. So sparse just means that most values of most features are 0 most of the time. So basically the intuition behind it is there are many possible attributes and most images don't have most attributes. This is not an obvious concept, so if this is not clear to you, consider rewatching the previous 2-3 minutes of the lecture and try to sort of convince yourself that this could be true. All right, but if we do accept this premise, then we have our job cut out for us. If we want this kind of structure, we have to figure out how to learn sparse representations, basically representations where the hidden state has most of its dimensions set to 0 for most images. Obviously not all of its dimensions, because it's very critical that some of those dimensions are non-zero, but they should probably be different dimensions for different images. As an aside, this idea actually originated in neuroscience, where researchers believe that the brain actually uses these kinds of sparse representations to represent things in the world. And this kind of thing has been verified experimentally. It's actually a widely accepted idea in neuroscience. If you want to learn more about it, look up something called sparse coding, which was actually discovered here at Berkeley by folks from Professor Bruno Olshausen's group. All right, so sparse autoencoder. This is going to be an autoencoder that learns these types of sparse representations. And the only thing we really have to do to get a sparse autoencoder is we have to choose a sparsity loss. So we're going to train the sparse autoencoder with backpropagation to minimize some loss function on reconstructing the input, but it will have an additional loss function applied to the hidden state that will encourage that hidden state to be sparse. Now, crucially, when we train sparse autoencoders, the dimensionality of the hidden state might actually be very large. So very much unlike the bottleneck autoencoder, the sparse autoencoder does not need to have a low dimensional hidden state. In fact, in many cases, we might have an extremely high dimensional hidden state, maybe even larger in dimensionality than the input, because the number of possible attributes that an object might have could even be larger than the number of pixels. This is sometimes referred to as an over-complete representation. Okay, so why might we want this? Well, because there might be a very, very large number of attributes, and in fact, the more attributes that we give the model, the more dimensions, the more sparse the representation can be. So we would like to give it a very high dimensionality. Okay, so we're going to call this hidden state H. And there are a variety of different sparsity losses that we can use. One of the simplest sparsity losses that we can employ is to just take the absolute value of each dimension of Hj and sum them up. It might seem a little peculiar that just minimizing absolute value makes the activation sparse, but the intuition for why this is true is that the derivative of the absolute value is a constant, right? So unlike Hj squared, where the derivative would depend on Hj, the derivative of the absolute value of Hj is always going to be 1 or negative 1, depending on the sign, which means that small values of Hj are pushed down, they're pushed close to 0, just as strongly as large values. But the large values are, of course, much more useful for reconstructing the image, so when we combine this kind of absolute value sparsity loss together with reconstruction, the network will tend to push the values of H that are already small all the way down to 0, and the larger values, they'll also be pushed down, but since they're so useful for reconstruction, they'll also be pushed up to aid in reconstruction. So larger values will remain large, whereas small values will be eliminated. This is sometimes referred to as the L1 norm of H, and its gradient is always the sign of Hj. If you think back to our earlier discussion of bias and variance at the very beginning of the course, we actually saw this kind of regularizer before when we talked about L1 regularization versus L2 regularization. Now, at the time, we talked about L1 regularization and L2 regularization on the weights of something like a logistic regression model, whereas here we're talking about it on the activations. But the principle is similar. In the same way that L1 regularization on the weights of a logistic regression model induces sparse weights, L1 sparsity loss on H induces sparse H. Now, this is not the only kind of loss that can give you a sparse representation. There are other kinds of losses or models. If you want to learn more about them, you can look up things like spike and slab models, lifetime sparsity, and so on. So there are many things that people have explored to get sparse representations that work in a variety of different ways. But the simple L1 norm is a very common choice, and it can work decently well. Things like lifetime sparsity can be a little more effective. Lifetime sparsity basically says that instead of minimizing all the activations all the time, instead you want every unit, every dimension of H, to be non-zero in a small fraction of the images. So it actually looks at the activations across the data set rather than minimizing all of them equally. And that can be a little bit more effective. All right, the last kind of autoencoder we'll talk about today is a denoising autoencoder. And a denoising autoencoder is actually one of the most classic and widely used types of autoencoders. It's a good model. The idea behind it is that a good model has learned meaningful structure should be able to fill in the blanks. It's a very similar idea to BERT. In fact, you can think of BERT as a type of denoising autoencoder. So the idea is that if you take an image and you corrupt it in some way, and then you ask your model to basically remove the corruption, then your model will have to learn something about what realistic images look like. Because if you were to just corrupt completely random images, well, there's no pattern there, so there's no way to remove the corruption. But if you were to corrupt natural images, it can figure out that things like edges and corners and semantically salient features like eyes and ears are present in real images, whereas the stippling white noise is generally not present. So if it learns to remove the white noise but keep the semantically relevant features, it will have learned something about what realistic images look like. There are many, many variants on this basic idea, and this is really one of the most widely used simple autoencoder designs. So there's not really that much more that I can say about the denoising autoencoder. It's very simple. It can be used to learn meaningful structure. It can be used to learn hidden states that you can then use as feature representations. And things like BERT can be viewed as a special case, as a particularly complex and useful type of denoising autoencoder. Okay, so just to summarize, the types of autoencoders. They all have some mechanism of forcing structure. Something about the design of the model or in the data processing or regularization has to force the autoencoder to learn a structured representation. This could be dimensionality, make the dimensionality of the hidden state small so that it does dimensionality reduction. This is very simple to implement, but simply reducing dimensionality often does not provide quite the structure we want. So if what you want is dimensionality reduction, it's great. If what you want is some sort of disentanglement that makes it easier to do, let's say, downstream classification, it may not give you the structure you want. It may actually lump together dissimilar things. Sparsity. Force the hidden state to be sparse, meaning that most entries are 0, so that the network has to compress the input. This is a principled approach that can provide very good disentangled representations with some very nice theoretical basis in neuroscience. But it's harder in practice because it requires choosing a suitable regularizer, and it requires adjusting the hyperparameters of that regularizer carefully to balance reconstruction against sparsity. So this can be a more difficult type of autoencoder to use. The denoising autoencoder corrupts the input with some kind of noise, forcing the autoencoder to learn to distinguish noise from signal. This can be very simple to implement, but it requires making a number of design decisions that are a little bit ad hoc. For example, it's not clear which layer to choose for the bottleneck, like, which layer becomes the hidden state? Which layer is most useful as the hidden state? Well, you don't know. You typically pick something like the middle layer, but it's a little bit of an ad hoc choice. There are many other ad hoc choices. How much noise to add? Where to add that noise? Why? So if you can make all these choices carefully, you can design a really powerful model, like BERT, but it takes a little bit of effort to figure out the right choices for your particular type of data and your particular type of model. The last type of autoencoder, which we did not cover today, but we will cover in detail on Wednesday, is something called a variational autoencoder. And a variational autoencoder performs probabilistic modeling. It basically connects up autoencoders to probabilistic generative models that we discussed in part 1 of this lecture. Here, the hidden state will be forced to agree with a prior, which allows us to use it for sampling. We'll talk a little bit about it in part 3, but then actually training these types of models will be discussed on Wednesday.